Okay, now you can hear me. So I have to use these more and more every day, old man. Um, okay, so in my announcement, I said I was going to start with a quick review of 8 and then move forward. Um, I'm kind of having to do this week a lot of asynchronous work. So actually, I'm going to do a review of 8 asynchronously. So um, maybe 8 and 9 together, although that's kind of that'll be a lot for one assignment. But probably next test will be 8, 9. So maybe I will do it that way. But in any case, so today's just going to be 9 beam profiles, and how we measure the beam itself. We've already measured the wave, we've measured the pulses, now we measure the beam. And also figure out we begin to understand how beams are steered and everything else, and how different focal points are created. So let me pause recording here. So I'm gonna, let me pause here. Hold on. Okay, guys. So I have my face blank because I'm using this as completely as a tablet, and it's not going to do you any good to look at my ceiling or the top of my head. So we're going to talk about the beams, and this is the really basic beam, a single element disc-shaped beam, which is it's a good standard for us to think about the future beams, where we'll talk about with multiple elements, perhaps many hundreds of elements, but this is just a single element discussion today. Let's just jump right into it. Shape of a sound beam. A sound travels, I'm reading on page 130 right here. The width of the beam changes. At the starting point, the beam width is exactly the same as the transducer diameter. The beam narrows progressively like a funnel until it reaches its smallest diameter. After that, the beam expands or diverges. Okay, so this is a really strange characteristic. Even a single element transducer creates a beam of sound. Towards the end of this chapter, we'll start to understand how this works, but it is unusual. If you have a speaker, you don't expect a beam of sound coming out of that speaker. You expect it to fill the room. But ultrasound is very different, and it actually has a lot to do with the size of the speaker, in this case the element, as compared to the size of the wavelength coming out of it. And that has everything to do with it. So it is possible actually to beam audible sound as well. You just need a lot larger equipment than what we currently use for ultrasound. So the anatomy of beam, we're going to look at focus, near zone focal length, or near zone length, far zone, and focal zone. Starting with the focus, so there is a natural point on a machine or with ultrasound where the focus just naturally occurs. So this is not changing your focal zone or anything. This is a natural focus. So we'll call this the focus. And I'm going to put in parentheses above it a natural focus. That's where it just wants to be. For a disc-shaped crystal, which is what we're talking about today, disc-shaped, like a penny. The width of the sound beam at the focus is 1/2 the width of the beam as it leaves the transducer. So, and this is, I'm just going to go ahead and throw a word at you that you'll learn a little bit later. Let's back this up. Use a different color and create a nice little pretty. First of all, it's the wrong color. And second of all, okay. This is the width or the diameter, I really should say. I gotta be careful because we're gonna talk about the diameters versus width in here in a second. So the width is also called aperture. Yeah, there's an A in there. Aperture. The aperture, or the width of the beam, or the width of the element. So the sound beam is coming out of the entire width, right? That makes sense. At the focus, with a disc transducer, the width of the beam is 1/2 the aperture. So the width of the beam goes from, so whatever this is, let's just say, let's just pretend it's 10 millimeters. So if this is 10 millimeters, the aperture from here across is 10 millimeters, then we could say that from here to here would be 5 millimeters. So that's, we'll just kind of, we'll put those in there as, so those are just example numbers. So that is our natural focus. Now, I'll just throw something at you really quickly. What happens to intensity? Assuming zero attenuation, just forget about everything else. Just look at intensity itself. Intensity would double because the area of the beam is 1/2 of what it was when it started. It's not just width, really. It's because it's a three-dimensional beam. The area of that beam is going to be 1/2 of where it started. So intensity is doubled. Let's just throw that in there. That's not really part of this chapter, but it's kind of a little bit of review from previous chapters, right? So then we have a near zone. Okay, I'm glad I drew 2 of these here. For a near zone, that's going to be everything from the focus to the aperture, or the aperture to the focus, I should probably say. So this is the near. I was thinking about spelling zone before I ended near. That's why the E ended out. Near zone, or also called the near zone length, at least the distance there would be the near zone length. But everything there is in near zone. Let's see, also called the near field or Fresnel zone. Near field, I'm not going to write field, but I will write Fresnel, because that is Fresnel, all right? Know both of those terms, near zone, near field, near zone, near field. You can kind of figure out that means the same thing, but Fresnel, that's that's a guy. He was an optics dude. I think he created like the lighthouse, or at least mirrors and stuff for the lighthouse. Anyway, also called near field. Beam gradually narrows or converges within the near zone. For a continuous wave, disc-shaped crystal, the diameter of the sound beam as it leaves the transducer is the same as the diameter as the active element. At the end of the near zone, the beam narrows to 1/2. So we kind of already mentioned that. So, you know, they just mentioned the term active element. I'll mess this up over here. The element or the PZT or the active element. In this case, this is a disc, like a penny or some kind of coin shape. And actually, for a coin shape, it actually creates a round in transverse. Of course, it would be round. Ooh, 9:58. You guys are 2 minutes away from starting your exam. Good luck with that. Okay, focal length. I kind of already mentioned that. I said the near zone length. So it's also called this the, let's put it back up here, near zone length, focal, also called the focal depth or near zone length. So focal length, focal depth, near zone length, all mean the same thing. As a length of distance, is the distance from the transducer to the focus. Certain characteristics of the active element discussed later will change that. So far zone is not just the best cartoon of all time. It is also everything from the focal point to near zone lengths. Here, let's make sure that's what they say here. Also called the far field or Fraunhofer. Okay, well, let's write these down. Far zone, far field, Fraunhofer. The far zone is a region that starts at the focus and extends deeper. Within the far zone, the beam diverges or spreads out. And by the way, it will continue spreading out and out and out. So our image quality goes down and down and down, actually. At the beginning of the far zone, the beam is only half as wide. Yep. From the focus, the beam continues to diverge when the beam is 2 near zone lengths from the transducer. The beam is again the same size as the active element. As depths more than 2 at depths more than 2 near zone lengths, the beam is wider than the active element. So let's see, kind of use my, right about here, I would say. Two near zone lengths, 2 of these. 2 of those. You get down to here, the diameter of the beam is now back to the original aperture. So if we were to drop, actually let's do that. Let's drop it like it's hot. All right. Let's see how well I did here. Oops. Right, where's my, yeah, it looks like I was pretty darn close. So at 2 near zone lengths, the width of the beam is now equal to the original aperture, the original width of the active element. We'll get rid of those just because it gets a little messy in here. Ooh, now focal zone is a region around the focus where the beam is relatively narrow. Reflections arising from the focal zone create images that are more accurate. Okay, focal zone is a smaller ruler, so more
accurate at the focal zone. Half the focal zone is located in the near, and the other half located in the far. You may note that the definition of focal zone is imprecise. Yes, imprecise. So let's imprecisely draw the focal zone. That's about right. Several mathematical descriptions of the focal zone are available, but not essential for us. The focal zone should simply be understood as a region where you have basically superior imaging detail. Okay. And the reason being, guys, is just like we want the, excuse me, just like we want the pulse itself. Now remember, this has nothing to do with pulses right now, okay? But just as we want the pulse to be as small as possible to create that small ruler, and I'm using air quotes, you can't see me doing that, and that small ruler, small objects, we also want a small beam diameter, beam width for measuring small things. Once again, you're not going to measure the common bile duct, for instance, if the beam is really wide. You just can't get, you cannot get precise information. It's, once again, a wide beam is like measuring an ant with a yardstick. Doesn't work. So small beam, thin beam as possible. Quick hint, in the future, small beams are not important anymore because of supercomputer, basically. Thus, the computer power is going up to such a huge degree that they're not going to be worried about super small beams anymore. But that is for another day. Okay, so summary. Wow, we're already at a summary. To clarify the concept of beam profile, the sound beam exits the probe and immediately enters the near or Fresnel zone. Yes, so in the first half, it's in the Fresnel zone. It gets progressively more narrow until it gets down to the focus, at which point the beam starts to diverge. So by the way, so this is a fixed focus transducer. We have no control over the focus. It just is where it is. And there are transducers that are like that. Fortunately, not our transducers. We do change our focus, by the way, guys, and it does make a difference. The focus marks the distance from the transducer, the focus column. You know what, let's just draw in a focal length. Green is pretty. A focal length, millimeters, whatever, you know, it will be measured in millimeters if we do measure it. It is the near zone. So these are pretty much mean the same thing. Focus marks the beginning of the far or Fraunhofer zone. So from the focus to really forever. This is a bit of a confusion point. Is a Fraunhofer zone just from here to here? Or is it here into infinity and beyond? All we need to know is that the far zone or Fraunhofer zone starts at the focus and then continues to diverge. Let's put this in. Divergent. Convergent. Okay. And there's an example here on page 133. Disc-shaped piezoelectric material crystal creates a continuous wave sound beam. Diameter of the active element is 12 millimeters, and the near zone length is 8 centimeters. The focal zone is 4 centimeters long. Based on this information, answer the following. Okay, well, let's actually draw that. Thank you. Gimme, gimme, gimme. Actually, elements. I'm just going to have to totally freehand the beam here, so bear with me. So I'm going to draw it, and sometimes I just put a little point where I know where the focus is going to be. A little helpful. Okay, kind of hit it. All right, that's actually pretty good. So let's see, the diameter was 12 millimeters. Okay, let's see, it looks like my point is there. And this is 8 centimeters, not exactly drawn to scale, but that's okay. And then let's see, there was a 4 centimeter focal zone. Okay. Well, let's see. What is the best estimate of the diameter or width of the sound beam as it exits the transducer? So right here. What is the diameter of that beam? Diameter is a diameter. It starts off at 12. What is the diameter of the sound beam at a depth of 8? Diameter equals, well, 1/2, right? Oh, let's turn my little helper off because it's not helping, is it? Okay, what is the diameter of the sound beam at a depth of 16? Let's see, 8. 8. Diameter, how did that turn blue? Oh, my hand hit it. Oh. Diameter here. This is 2 near zone lengths. It has gone back to 12 millimeters, right? What is the depth at the focus? 8. What depth marks the beginning of the focal zone? What depth marks the beginning of the focal zone? Ooh, I almost just rattled off a number without thinking. Focal zone. 4 centimeter focal zone. That must mean there's 2 centimeters there and 2 centimeters there, right? Because this is the middle of the focal zone. So must be 6. And yes, the answer is 6 to the beginning. So if I put a 6 centimeters here. Okay. Easy peasy. Determining focal depth. Yes. Do I even want to read? I better read this. Focal, page 135, guys, if you're following along. The focal depth, also called the focal length or near zone length, is the distance from the transducer. Let's see, 10, 12, no texts. So good. Sounds like everyone got in okay. Also called the focal length or near zone length. Is distance from the transducer to the narrowest part of the beam. Most modern ultrasound systems allow the sonographer to change the location of the focus. So we change from a natural focus to something else. We force it to focus somewhere else. But those are on phased arrays, multiple element transducers. However, early in development, we couldn't do that. What characteristics? So basically, we're still talking about single element transducers and how we make those changes. Okay, so let me pause here because I want to make this a little better. Okay, I moved my little transducers over, gave myself a little more room on the overall sheet as well. Okay, so we're going to talk a little bit about the profile of a transducer and how, or a transducer element, and how that affects the depth of the natural focus. Now this all matters, even though we don't use elements like this, it still matters because aperture, width, frequency still affect the natural focus of multi-element transducers. So that's why we have to learn about single element transducers first. So anyway, how does the, page 136, how does the transducer diameter affect the focal depth? So the diameter and focal depth are directly related. Okay, so here I have a narrow diameter. Little helpers. A narrow diameter versus a wide diameter. And how does that affect? Well, I'm going to put a little bit of a cheater here. And diameter, so there's my focus. Okay, well, more or less. So I have just guesstimated, guys, the distance typical for a near zone length. Get that off for a second. Near zone length of a narrow diameter transducer. Now let's estimate the distance for a, oops, that seems about right. Okay. And once again, we'll draw in a near zone. Oop. Okay. So graphically, all I'm showing you here is that if you have a relatively small transducer diameter, so your element diameter is relatively small, that forces the focus or the near zone length to be a little closer to the transducer itself. A wider transducer or wider element will force the natural focus to be a little farther away. So that's one thing to think about. The other thing is a little less, doesn't quite make as much sense to us, and that is lower frequency versus higher frequency. So the imaging here is a little bit, jumps ahead a little bit, but the beam profile is exactly on page 136. Let me just give you a little hint as to why this beam up here, let's make this transducer element, I'll try to make it pretty. Man, okay, and it didn't work. Is a lot thicker than this element. So this element is thicker, not diameter. We've got to make sure, we have to be very careful about thickness and diameter. In fact, these two diameters are the same because I copied one, put it over here, and then I squeezed it. Or vice versa, I can't remember. But thickness is this direction, okay? As you might imagine, if you think of the Liberty Bell, if you were to see a cross section of the Liberty Bell, perhaps the metal would be about this thick. And the sound, of course, would be a low frequency sound, like a gong or a deep sound. Whereas the thickness here is very thin. That's more like a very small bell, or maybe even a piece of crystal is going to be represented more by that. That's going to create a high frequency sound. So let me draw out the beam profiles of two transducer elements, same diameter, but different thicknesses. So this one's a low frequency here. Let's get my little cheater. And I want this guy to be about here. So, okay. Let's move my cheater over to the high frequency. That's about right. Okay. So once again, you see that there's a difference in the natural focus. Now, this is really unexpected if you think about it. Low frequency, we've already learned that low frequency is used to go deep into the body. And high frequency is used to go shallow into the body. So wait a minute. Why is high frequency, why is the natural focus, and it looks like my natural focus is right about here on this one. Why is my natural focus there and not up high? Well, it's just that the physics of creating a beam profile don't agree with attenuation. They're completely different things, and so the beam profile is the beam profile. And a higher frequency transducer creates a longer near zone length. Let's draw this in again. Near zone length. Near zone length. So that's a conundrum. What are we to do? Well, if you're building a high frequency transducer designed to go shallow into the body, well, it has to be a thin element. It absolutely has to be a thin element to create a high frequency sound. Well, you would combine then a narrow, let's get my pretty green here, a narrow width with the high frequency. And if you combine those two aspects, hopefully you get a natural focus that's a little closer to where you want it to be. If on the other hand, you have to use a low frequency transducer and you want the natural focus to be deeper, well then you have to use an element of that thickness to create the low frequencies, but you also have a large diameter transducer, and hopefully you can create a natural focus which is appropriate for your needs. He mentions that on page 137. The fact that higher frequency sound creates a deeper focus is particularly troublesome to sonographers. The rule of physics is higher frequency creates a deeper focus. Transducer manufacturers are aware of this, bad at physics, and overcome it by making very small diameter, high frequency transducers. Yep, so they combined the best aspects for what they need out of that transducer. Even with high frequency sound, an extremely small diameter displaces the focus shallower. This combination creates a clinically useful transducer. In soft tissue, the equation that describes the mathematical relationship between diameter, frequency, and focal depth is as follows. We only worry about the top one of these two. So let's just go ahead and I'm going to draw it in over here. Oh, actually, this is a good place. Good as place as ever. Focal depth. Focal depth in millimeters is equal to the diameter millimeters squared times frequency in megahertz and divided by 6. I'm not sure why the number 6 is there. I haven't figured that one out. Oh, I bet I could figure it out, but I'm not going to. All right. So diameter squared times the frequency will give us our focal depth. Diameter squared, once again, when something is squared, it kind of has more meaning. So that diameter, change in diameter makes a bigger difference than the change in frequency. And does this make sense? Hold on. Let's see everything at once here. Focal depth. Okay, so if we increase the diameter, we increase the focal depth, and yes, that works there. If we increase the frequency, we increase the focal depth, and let's see, this was a higher frequency, so yes, that works there. And if you do both at the same time, then you have a very deep focal depth. Okay, yes, everything works. Cool. It always works out. I mean, it's always good when things work out. I'm going to skip these questions and probably use those as part of our next asynchronous assignment. The diameter of a sound beam is smallest at the end of the near zone, the focus. I'm sorry, on page 139, we're going to talk a little bit about beam divergence. Deeper than the focus, a sound beam spreads out or diverges. What characteristics of a transducer determine the spread of the beam? Diameter and frequency. Dun, dun, dun. How does transducer diameter affect divergence? Okay. In any case, when we are looking at a short, this rule works with both frequency and diameter. The shorter your near zone length, the faster the divergence. So they kind of, you know, you can exaggerate it a bit. And we could actually see this, at least I can notice it when I'm looking at when we bring our focus up high, the far field on the screen, the Fraunhofer zone on the screen, the quality of the image goes down pretty quickly. Well, that's because the beam width is diverging quickly, and the fatter the beam, the less quality image you get. You want to keep that beam as narrow as possible. Anytime the near zone length is longer, the beam divergence is a little slower. Okay, so this was diameter, right? So short diameter, short focus, more divergence. Wide diameter, longer focus, less divergence. Same thing here. This guy is diverging faster. That was a low frequency. Let me just slow down, make sure I'm saying everything correctly. How does the transducer affect me? Diameter, and yeah, I mean, all I gotta do is look at the picture and know I'm saying it correctly. Low frequency. Creates a short near zone length and more, a little faster divergence. High frequency, longer near zone length. Divergence is still there, but it's not as fast. And guys, I don't really want you to think about the sine divergence angle is equal to 1.85 divided by diameter times frequency on page 140. Not worth our time. Simply not worth our time. Improve lateral resolution. Let's see, 10:30. Oh, you guys are definitely still taking your test. Okay, so that was pretty. Just slam through a couple of pages real fast there. Okay, this is my favorite part of the whole book right here. Well, hopefully I could do this on my program here. Spherical waves, page 142. We're going to start to understand how a beam of sound is created rather than a spreading out sound like we normally know it to be. Sound waves produced by very small sources diverge in the shape of a V. The V-shaped wave is created when the sound source is about the size of the sound's wavelength. So that's why we don't see this on a daily basis. For this to happen, we would need a gigantic element or a gigantic speaker because the wavelength of sound that we hear is so much greater, orders of magnitude, millions times greater than ultrasound. And so we really have a hard time with a single speaker or a single element creating a beam of sound in the auditory range. It's really impossible. There are other ways of doing it, which we'll learn probably chapter 10. Oh my God. I'm way ahead of time here. Okay. Anyways, these V-shaped waves are known as spherical waves, diffraction patterns, or Huygens wavelets. The small sources of sound producing these wavelets are known as Huygens sources. So, and yes, I looked up how to pronounce Huygens. We have learned there's actually a deep space probe called Huygens. I forgot where it went though. We have previously learned that ultrasound transducers with large PZT crystals create sound beams that are shaped like an hourglass. Okay, well, hourglass meaning We've learned that with large PCT crystals. Well, I mean, it's more hourglass-like with the small PCT crystals, but however, small sound sources create beams that are V-shaped. This apparent inconsistency was explained by Christian Huygens, and is known as Huygens principle. In other words, yeah, I mean, if sound is coming out of here like this, I mean, that's what we should expect, right? That's how sound normally spreads out. But that's not how it happens. The hourglass shape produced by a large crystal is a result of interference. Constructive and destructive interference. Many Huygens sound wavelets emitted from these numerous sound sources. Okay, so Huygens figured out that a single element, when we're talking about where the element or the sound source is much larger than the wave itself, it doesn't act like a single source. It acts like many, many sources. So I've kind of started something here. Hopefully this all works. And make sure that we're good to go on that. So a single element, one element, acts as if it's millions of elements or millions of different sound sources. So that's a little weird. What I'm going to do is I got to capture this first row. What I've drawn here, these circles that I've drawn, are essentially a representation of all these hundreds, if not millions, of sound sources. So each one of these, each circle represents an individual sound. Actually, let's move that up just a little bit so it's kind of buried. And that's better because it's, so this is the sound as it's first emanating from the transducer. A moment later, a second later, another sound source, the waves move out. I'm not sure exactly how this is all going to work out. I only thought about this, didn't actually do it though. Actually did a, some schools will do a project for, what's it called? The SDMS yearly meeting. And I did a poster project depicting this, and my instructor was so excited. It was really great. And the problem is I did black lettering on a blue background, and you couldn't read anything on it. So it was very, very frustrating. Okay, I'm sorry. I know this is taking a little bit of time. Here, I'm going to pause. Okay, so I stopped recording. I have some visitors. We have some new students. We have some of you guys are on. Some of you guys are still taking the test, and others will probably opt not to look at this at all right now. And all that is fine. In the meanwhile, I crashed my computer because apparently moving things takes a huge amount of information. So I'm going to have to hit Control Save a lot because I did lose some information. I had to start over again. It was a little frustrating, but that's okay. We're here now. So let me write out this this word here. This guy's name is Christian Huygens, and what he discovered
is that even a single element, so guys who are just joining us for now, we're talking only about single element transducers. It's not what we use, but it's a very good starting point to understand how the beams are created and how we steer the beams and change our focus and all that. It all comes down to Huygens. So what he discovered is kind of interesting, is that if the element, if the aperture of, aperture is the width of the element, if that width is considerably more than the wavelength, then you get what occurs is that the element acts as if it's thousands, if not millions of individual elements, all pulsing sound or creating sound at the same time. So it doesn't act like a single sound source, it acts like many sound sources. Now, just a few minutes, well, in this video's time frame just 2 minutes ago, but for me it was more like 20 minutes ago, I was just talking about how you couldn't really do this with auditory sound, because the sound that we hear, the sound of my voice, that wavelength is enormous, by millions of orders of magnitude bigger than ultrasound. Ultrasound has tiny, tiny little wavelengths. And so it's very easy to create a sound source that's much larger than the wavelength of the sound. Whereas to do that with an auditory, we would need a sound source as big as Mount Everest in order, well, maybe not that big, but still, it would have to be very large in order to create, as big as a building, to create a sound beam in this way. Now, we do create sound beams in different ways with auditory. The military has some pretty cool stuff where they can beam sound, but that actually kind of goes into the next chapter or two on how they would do that and how we do it, actually. So anyway, Huygens discovered that a single sound source, if it's large enough compared to the frequency of sound, or in other words, the wavelength of sound, that it acts as if there's millions. And so what I've drawn here, it's a little bit messy here, but I've drawn multiple sound sources going all the way across the single element. So this is like a single element, it's kind of like a coin, like a penny. And this is a round element. And then when I started drawing here, why? There we go. Now, unfortunately, this is what crashed my computer before. So I'm gonna do like one of these and then I'll talk. And then I'll do the other one and I'll talk. And I've done something like this in the past. I honestly don't know if this is gonna work for us. But what I'm showing here is a kind of a time lapse of this sound. Let's say it's a pulse of sound coming out. And as it comes out, of course, the waves, individual waves, spread out because that's what they do. They're traveling. I don't, oh, no, there. Control Z, Control Save. Okay. Oh, I'm going to regret that. Control Z. Oh, damn it. So unfortunately, this is better suited if I didn't realize it was going to take me this long to do this. I wasn't expecting the problems that I have. Okay, I'm going to stop there for a moment, let the computer catch up. No. Control S. S and the Z look a lot alike. Okay. So what I'm beginning to show are these wavelets. I can write the word wavelet without crashing my machine here. Huygens, well, okay, Huygens. So we have this individual with sound source here begins, and it comes out, and it comes out, and it's kind of, this one's actually, should be showing a little spreading out more, a little more like that. So this is not 100% accurate, but in other words, as a sound source begins, there's our transducer, it's going to be spreading out like that. Well, wait a minute, I just said that we're creating a beam of sound, that it's not spreading out. Well, so when it ends out happening, maybe I'm better off just drawing it like this, is that we have another sound source here. It's a different color. And that one produces a wave that individual wave is spreading out as well. And then we have another one over here. Actually, all my work, and I think this is better. And this guy is spreading out. And we could see what's happening a little bit. This isn't drawn that well, unfortunately. It's red as you have areas where the wave, and wave are converging. These are basically, every line that I've drawn is the amplitude, is the peak. So these wave peaks and troughs are in between. Troughs are not drawn in, but they're just kind of in between the wave peaks, of course. I got 3 waves right here crossing over each other. I have it here. Well, I kind of messed up, and I have 2 here and 2 here, but those really should have been a little better drawn. But I also have really nothing crossing out here. Maybe one little wave crossing here, but nothing here, maybe something there, nothing there. And if I were to draw this a little bit better and thought about it a little better, well, I can also show waves construct. So this is all where the waves cross like this is constructive interference. And what ends out happening is that you get constructive interference in the middle of the beam, in the middle of all these waves crossing over each other. Most of, not all, but most of the constructive interference is right dead center in front of the transducer face. In other words, and it keeps on happening. The farther and farther down you go, those wave fronts continue to overlap each other. And what happens out here on the edges is that the wave ends out being very weak because there's no constructive interference, and sometimes the destructive interference, which, by the way, purple, destructive interference would be like right here, because that peak is traveling over trough. So that's actually destructive. Here, we'll color that in as destructive. It's just out here, that's destructive because this peak, that green peak peak is traveling over no man's land in between other peaks. So that's destructive. So we have this combination. So most of the destructive, or it's either destructive or no interference at all, occurs on the outside. So that part of the beam becomes very weak. In fact, it becomes insignificant. I can't say all, most
constructive interference occurs right dead center. There's little GIFs. There's a bunch of little GIFs actually. I can show you guys on how that works. In fact, what time is it? It's only 11 o'clock. Now in that case. Yeah, I'm going to go ahead and let's just take the time to kind of, I'm going to draw this out again. Be a little more careful this time. I'll create a transducer face there. Create little, So a number of different sound sources here. I'll just use one color for all of this. Each of these sound, and so that's a sound source. So, you know, I made a circle because it's easier, but I'll make half circles here. I know this looks like it's going to be a mess, and I will use different colors. And what ends up happening, and once again, this is not as pretty as it could be, but it's actually going to work out just fine. So we end up getting a beam profile, which looks a lot like this. Oops, let's not do that last one. Where there is sound outside of the beam, it's actually really inconvenient for us. It causes a whole lot of problems, that sound outside the beam. And outside the beam, there is some constructive interference, but not a lot. Whereas inside the beam, constructive, 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 all of this is interference every time these cross over. And so I did some kind of research, literally just drawing this out and using, what I did is use a string and a pen, and I would just draw these out and draw these little semicircles out using the string, and then I would make the string longer and draw the circles out. And I could see what was actually happening. At some point in the focal point, this wave front, and that's actually a good word for you guys to. This wave front becomes so flattened that at the focal point is the point at where it actually, that's not how I wanted to draw that. Let's see, it goes, yeah, the wave front starts coming down kind of in this pattern, a little bit like the bow of a ship. And then at this point, it's coming down and it kind of flattens. And then at some point, it actually spreads out this way. And it really has to do with how these waves interact over time. And I actually worked it out graphically, not mathematically, of course, you guys know me. But graphically, I was able to work out how that happens. It's kind of interesting. So, and you missed the first part of the, if you're watching right now, you missed the first part. And so what happens is a sound beam comes down to a natural focus, and then it starts to spread out a little bit. And the spreading out has to do with how these, over time, kind of almost the wavefront inflects. And once it inflects, it's still all traveling downwards, of course, but down here it's starting to spread out just a little bit. Okay. Huygens. Okay, so this isn't really important for us to know. I will give you a hint at where we're going with this. Unfortunately, I'm pretty much at the end of chapter 9, and I don't necessarily want to go into chapter 10 yet. The hint at where we're going is this. So this is a representative of a single element transducer that acts like it's thousands of elements. So what did engineers do? They created thousands of elements, or at least hundreds of elements. And so by creating a system where we have element, 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 this going across, of course, these are all supposed to be the same size and right up next to each other, but you get the idea. We're now able to have a lot more control over Huygens wavelets by precise timing of each and every element. So with a single element, it's one zap of the machine and the whole element vibrates, creates a sound, beam of sound. With our transducers, we have many elements. Each one of them is very precisely timed. And if we time things really well, we can take our color box or even our whole grayscale beam and point it to the right, or point it to the left, or bring the focus up closer or farther away. All of these things are done by using Huygens wavelets, but the way we're able to control that is by many elements working almost, well, not independently, but like a concert, though. They're working together, but at slightly different times. Okay, so I don't know. That's all of chapter 9. So let's pause.